Good morning, this is Jean-François from Chrysalide Engineering. I'd like to share a project which was used to power up a device depending on the ambient light. And this project is to keep a device shut off at night and power up at day, have some control over the luminosity required to power up. Also note this project is available on the website, including the firmware and hardware files for the Kicad and microchip MPLab project. Over this address, lc/downloads, under the description, and this link. What you'll find out is this schematics and this PCB layout. And we can see that the design includes just 12 volt terminals, provision for a switch at the low voltage side, which is the external load, but the board itself will remain powered up through J3 going to the LM7805. We create a 5 volt rail. We measure the power supply voltage, which is nominal 12 volt, but as a battery supply we can get from 10.4 to about 13.5 volts, more or less, or up to 14 volts. So say between 10 and 14 volt is the range. And then we have an onboard phototransistor over here. The used device is this one on board, FH309FA4, which provides 1.1 to 1.8 milliamp at these nominal conditions. We are providing the VC of 5 volts. We see the operating range is minus 40 to plus 100 degrees C. VC max 35 volt. Collector current 15 milliamp. And it's for ambient light 900 nanometer. And that's the curve for the light it can detect. And the orientation. We see the amplification factor depending on light. And the microcontroller we use is a 16F628 from a microchip. It's more than enough for this small project. And we will use a comparator mode with this mode 010, which is actually we have two pins, AN0 and AN1, connected to our supplies we want to measure, because we don't have analog converter, we don't only have these comparators. And we will use the VRF from the module. So looking at the schematics, we have the phototransistor going to a BC547, and we see that this design depends on the amplification factor of this BC547. So it depends on the type and make, it depends on the temperature. So it's not a pretty stable design, but good enough for this purpose. If you want more stable design, then you need probably a proper detection circuit. This can be calibrated to work on the conditions we want, basically. But then it varies a bit depending on the ambient temperature, essentially. But it doesn't make a big difference because this sensor provides quite high current, so when we have the transition, it's going to be easy to detect the transition, so we don't have any issue. And we see a potentiometer to select what ambient light we want to switch. These values have been tested on the prototype product, so there we have 220K and 1K, and we get VL to analog 1 and VB, the battery, to analog 0, and we are using roughly 1.8 up to 2 something volts detection voltage. And we see that both of them are using the same VRF internally, so that's why we calibrate over this transistor, and these particular values are used, which make analog 0 and 1 usable with the same internal VRF. So we have these two comparators, C1 V out, C2 V out, and we are going to check in firmware what is the status of this, and we are going to make an hysteresis. And we see the code over here. We enable the comparators, we set them with the proper VRF, and we can switch the VRF from 1.87 volt to 2.03 volts, and therefore we can make an hysteresis. Essentially, when we detect either of the VRF, then we will put the hysteresis, the voltage high, and power off the load. And when the lights come out, we will get the detection threshold back to low and power on the device, and we make this loop every 500 milliseconds. This is very rough code. We have a detection only every 500 milliseconds, and that's good enough for the purpose. This delay is not exactly accurate. Depends on what was done before. So back to the schematics, we see that we want to take care of what is the voltage on the battery. And when we have good voltage on the battery and a low light, only then will we put the Q3, which is a BD139 transistor, to active and essentially close the LV section. And the LV is the output. We have the LEDs just to display the status like this. Is the battery okay, and are we in day mode? So when we detect light and the battery is on, we have both of these LEDs on. And that's all for this schematics. It is fairly simple design, and we see this is documented for the code implementation in here. And we have the microcontroller, and we have everything we needed on this simple schematic. We see the layout. It is fairly small, but we are using a through hole, and we see the transistor, and this is actually Q1, so the provision for the phototransistor, the terminals, voltage regulator, power terminals, potentiometer, microcontroller, and the power output transistor. So this board, the full schematics and PCB layout is available on the download link under description, as well as the code, so you can essentially make this or a variant of this board if you like for some of your projects. This design can be optimized, but it was made just for CNC routing. So essentially we have a single layer design, exception for these two bridges, which can be done through jump wires. So it's mostly a single side PCB design. In code we can see we are using an external clock. This seems to be wrong actually. The configuration bits showed a watchdog timer and external oscillation circuit. I think it is not accurate because we don't have it, so we need internal clock. As well, we don't reset the watchdog, so we will need the watchdog to be off, and we will need to change the oscillation mode. The other parameters seem to be fine. The user init is simply the LED, the outputs, LEDs, and transistor control. The analog reference to be set. And we have a delay function. In the main code, we go through initialization. And then we just have this while loop with a 500 millisecond period to check what was the comparator output. And according to the status, we put power on or power off and set the LED appropriately. We sell some of our boards on the website, which you can visit and check. And if you had these downloads, you can get this project and a simple bug power supply as well. And you can even subscribe if you want to keep informed on new projects will be added to this list. These are completely free projects, so sharing for community. And regarding this project, remember that you have to do some testing with the clock if it was fine for your case, or you perhaps need to modify this parameter. Thanks, and keep in touch.